Alright, hello everyone and welcome to a new practice session for the time complexity chapter. As you can see here, we have again a function, print numbers, which has an argument n. And yeah, again, as the name suggests, it prints some numbers. So let's see how it does this. First of all, as you can see, we have a for loop, right? And it prints all the numbers from 0 to n minus 1. Then we have I equals 1, so it basically resets the value of I to 1, and as long as I is less than or equal than n, it prints that value and then multiplies I by 2, continues, and so on and so forth, until I becomes greater than n. Cool. So, again, another quick example, just to make sure that we understand how the algorithm works. For n equals 8, what happens here? Pretty simple, right? Each value from 0 to 7, we print it, right? So we print 0, we print 1, we print 2, we print everything until 7. And then what we do is that we start from 1. 1 is less than or equal than 8, right? So we print 1, again, 1, multiply by 2, still good, print 2, print 4, print 8, and then 8 becomes 16. And we get out of the while loop, right? So yeah, these are the numbers that we are going to print for n equals 8, right? As you can see, these numbers are basically formed by two sets, right? By two groups. This is the group that the for loop printed, and this is the group that the while loop printed. So, if we take a look at the whole algorithm, we will actually notice that it consists from two sub-algorithms, right? So this is the first step that we always do when trying to compute the time complexity of some algorithm. We see if there is multiple sub-algorithms that are basically independent of each other, right? So we obviously have a for loop here and the while loop here, but they are independent. It's not like the while loop is inside the for loop or the for loop is inside the while loop, right? So the first thing that I'm actually going to do here is that I'm going to set the first sub-algorithm, which is only this for loop, right? And set the second sub-algorithm, which is this while loop. Perfect. Now, because they are independent, I'm going to compute the time complexity each of them has. And then, of course, I'm going to add those time complexities together and obtain the final time complexity, right? So, first sub-algorithm, as simple as this. I have a for loop going through each value from 0 to n minus 1. How many values are in this range? Obviously, n values, right? So this for loop performs n iterations. So n iterations. And on each iteration, I just print a value which is constant. So the time complexity of the first sub-algorithm, right? Let me do that so I can have more space, is big O of n, right? That's super simple. Cool. Now, if I take a look at the second sub-algorithm, I starts by 1. For as long as I is less than or equal to n, I print it and I double it, right? So it's something that we've seen a lot, right? By now, I start by 1, 2, 4, 8. It's always doubled, right? So I is always going to be a power of 2, 2 to the power of 0, 2 to the power of 1, and so on and so forth, until, of course, I reach 2 to the power of some k, which is still less than or equal to n, right? And 2 to the power of k plus 1, the next one, is gonna be too large, right? And this k, we know it is log of n, right? So 0, 1, 2, log n are my exponents. So the number of iterations my while loop does is exactly log n plus 1. So I have here log n plus 1 iterations. Constant, constant, constant. So I can conclude that the time complexity of the second sub-algorithm is big O of log n, of course. We don't care about the constants, right? So, as you can see, I have an algorithm that consists of two sub-algorithms, first one being executed in big O of n, and the second one being executed in big O of log n, right? So what I have to do is, of course, I have to add this together, right? So I can say if we add them together, big O of n plus log n. But that is not correct. And we know why, right? Because this is a polynomial, right? Or an expression, however you want to call it. And when we have an expression which consists of multiple terms, right? And each of them depending on n, we are going to take only the biggest one into consideration, right? So again, if we think about the graphs, right? This expression is obviously first term n, second term log n, right? The graph of n is obviously like this. This is value of n, and this is big O of n, right? When n gets bigger and bigger, big O of n gets also bigger and bigger, right? But if we take a look at the graph for log n, so this is the value of n, and this is actually big O of log n or log n, no worries. The graph looks like this, right? It gets increased, but really, really slow, right? So which one is more important? For example, when n equals 1 million, right? It's going to be the value from this graph when n equals 1 million, or the value from this graph. Obviously going to be n, right? So again, for example, for n equals 1 million, this n is going to actually be 1 million, 10 to the power of 6, and the log of 1 million is going to be 20, right? So when I have a time complexity and one factor, one term give me 1 million iterations and the other only 20, I don't even care about the 20, right? That's too few to even care about. So yeah, those are the two things that I was really interested in showing you again. The sub-algorithms stuff, you add them together. Yes, you do that. But after adding them together, in order to get your final time complexity, you always look at this expression and take the factor or maybe factors, who knows, we're going to see, that is really the most important. And here n really trumps the log n, right? Log n is not important. So the final time complexity of this algorithm is big O of n. Awesome. Cool. Congratulations. Practice 4 is finished. I'm going to see you on the next one. Bye.